Should the unitaries be from like Cn to R2n or something?
Wait a minute. The unitary?
Should it be from Cn to R2n? Because
Cn to R2n, why? U1 and U2 are you? This is a whole statement is about, see, given a in M and R, you get an operator SA. SA is from Cn to Cn.
Oh, SA is from Cn. It's
Yeah,
not what we defined earlier.
No, we defined SA, but so that SA naught is defined like SA is defined from Cn to Cn. SA naught is. Earlier, I defined SA to be using complex. I mean, this is just for convenience. We have just written like that. Okay. So SA is defined on Cn. So that SA naught is the corresponding. I mean, there is a one-to-one correspondence between operators on R2n and Cn as real linear maps. Okay. We are just using that correspondence. Now, if you have a symplectic, any arbitrary symplectic map, then there exists unitaries and a SA such that this happens. So these are all statements about Cn, okay, where A comes from M and R. So we want to prove this. We want to get this. So maybe I will digress a bit whenever. So one thing is, if you want to make any statement about real linear space, real linear operator, if you have a real linear operator, you can extend to a complex linear operator. I mean, if you have on the complexification by only one way. If you have a R defined on some H, R on B of H is real Hilbert space, suppose. Then you can define on H plus IH, which is the complex Hilbert space. You only have to define on IH. There is only one way. You have to take R of, it has to satisfy this relation, complex linear. So it has to satisfy this relation. So you can only define as X plus IY as Rx plus IRY. Okay. So it's like, so then you can verify that will be complex linear. And if you have some properties, you can see which properties you can bring from there. Okay. One such thing is spectral theorem for, I don't want to go through that. Okay. I think that can be proven through that, or otherwise also it's well known. We are only using for matrix. Okay. Any symmetric matrix can be diagonalized. Real symmetric matrix can be diagonalized. That's what I'm using. Okay. That is well known. Okay. Before that, I want to use polar decomposition. Polar decomposition might be a bit tricky, but here it's easy. Okay. So first digression. Let me make a digression first. Digression is for any. So any R in, so we want it for R2n, but let me say for any, I mean M and R, for any M and R can be written as, I mean, there exists polar decomposition for any R in M, for real linear operators. That's what I want to say. Okay. So for that, I assume, okay, I write it for S naught itself, because I don't want to prove for general operator. I just want to prove for the invertible operator, which is very easy, direct. Okay. So digression. So there exists a unique polar decomposition. For S naught. Okay. S naught is a real linear operator. So S naught is equal to, there exists a unitary U times some H naught. Okay. Where U is unitary, real unitary, of course, unitary in R2n, and H naught is positive. That is positive means, let me just write it again. X, H naught X is greater than or equal to 0 for all X in R2n here. Okay. H naught is an R2n operator. This positive, I mean, we want a positive operator A in M and R, that is different. But here, this is just a polar decomposition I am stating. I will first prove the polar decomposition. And H naught is symmetric. H naught transpose equal to H naught. Okay, that is what positivity means. So we want to get an operator like this. Okay, proof of polar decomposition. Okay. S naught, we can always write it as, so for S naught, define mod S naught. S naught transpose. So to differentiate between complex linear, I am just using transpose to take S naught. And this is a positive operator. S naught transpose S naught is clearly symmetric. Of course, the transpose is itself. And you can verify it on inner product that it is positive. So it's a positive operator. So if you have a positive operator, you can extend to a positive operator on the complexification. There you have a square root. You can actually prove that that square root will give rise to the, I mean, that square root will be of the, will come from a real linear operator, and that will be like this. Okay, just verify this. You verify that this is positive. This is S naught transpose S naught is greater than 0, and there exists a square root, unique square root, of course. Okay. By going to the complexification, you can verify that this is not difficult. Okay, S naught is this. Then we can write S naught as, and also verify that this mod S naught is also invertible operator, because everything is invertible there. Okay. Square root of an invertible operator is invertible. You can prove that. Okay, by using the relation itself, you can prove. So if you use all that, you can write it as S naught mod S naught inverse mod S naught. You can write it like this. Okay, so call this as unitary. So I want to say U no. So maybe I'll write U naught. Okay, U naught. I put U naught there. U naught times mod S naught. All we have to verify that S naught inverse is unitary. Okay, but S naught mod S naught inverse X, S naught mod S naught inverse Y. Okay, this S naught you can take it as a star there. So which is just S naught star S naught mod S naught inverse X mod S naught inverse Y, right? But S naught star S naught is just the square of mod S naught, right? So one mod S naught will go away. You will get mod S naught star mod S naught there, which you can take it as on the other side, because it's positive, it's symmetric. You can take it to the other side, and that will cancel. You will get this is equal to XY. So it's unitary, and it is invertible, so it's unitary, right? Should I write the whole thing? It's clear. Okay. I'm just using the star property and then the actual definition of mod S naught. Mod S naught is just the square root of that, right? Okay. So
and like it's invertible only because S naught is invertible.
Correct, because S naught is invertible. Yeah. Okay. So this is clearly, this gives a polar decomposition. We want to prove it's unique. I want to prove it's polar decomposition is unique. That's what we want to say. So it's unique. So suppose S naught is also equal to some V naught times some H T naught. Okay, with V naught unitary and T naught positive. Okay, then you just take S naught star S naught. You just take it. That will be T naught star is T naught because it's positive, and V naught star V naught T naught. So this is just equal to T naught square. Okay, so this implies T naught is nothing but mod S naught itself. Okay, mod S naught itself, right? By the same property. So this implies what S naught is equal to V naught of mod S naught. Okay. Now we have to prove that but this is clear because it's invertible. You can take it to the other side. V naught is nothing but A naught S naught inverse, right? There is nothing. It's just tautology. Just write the definition. You get this. There is no other way. This is only for invertible operators. Otherwise, you need to work with partial isometry and other. So this is because it's invertible, it follows direct. Okay. So that is what. So polar decomposition is proved. So we have proved the polar decomposition. So, but we want to prove this theorem where any symplectic isomorphism is given by a unitary multiplied by a unitary on the right and left. In the middle, you have a SA. That's what you want to prove for A positive. Okay. Now theorem of proof of the theorem. The theorem or proposition. I don't know what I wrote. Okay. Okay. So let S naught equal to U naught H naught be polar decomposition. Okay. Then we have S naught is symplectic. Okay. So J S naught J inverse is equal to S naught star inverse. Okay. So which is equal to on the other side, if U J U naught. Yeah, but what is S naught star inverse? S naught star inverse is, I mean, you want to take the star and then unitary star inverse is unitary itself, right? And for positive operator, for in self-adjoint operator, star inverse is just inverse. Star is, there is no star. So S naught star inverse is equal to U naught H inverse. U naught H naught inverse. That is what S naught star inverse is. On the other hand, I evaluate this J S naught J inverse, which is equal to J U naught H naught J inverse, right? Which is same as J U naught J inverse J H naught J inverse, right? Okay. But then that's a unitary. J is a unitary. So J U naught J inverse is unitary. Okay. And if you conjugate a positive operator by a unitary operator, it's again positive. Okay. I mean, the conjugation by a unitary is a very one of the nicest isomorphism you can have. So because of that, so this implies this is unitary. And this is, what is it? This is positive. Okay. So U naught H naught inverse equal to this. So these two are equal. Okay. So by uniqueness of polar decomposition, U naught is equal to J U naught J inverse, and H naught inverse is equal to J H naught J inverse. Okay. So in particular, this implies U naught and H naught are also symplectic. Okay. Okay. So you have got a U naught on the left hand side, which will be part of that U1. So we only have to deal with H naught. We have a positive operator, positive symplectic operator. Now you want to write that as in the above form. It's enough to write that in the above form. Now we want to deal with positive operator. So H naught is a, of course, H naught is an M, 2N, R. Okay. And it's positive. In particular, it's symmetric. Okay. Symmetric. So there exist eigenvalues. Okay. Positive eigenvalues. Lambda I. Okay. I don't want to index is I equal to 1 because for the reason I'm good. Maybe I in I. Okay. I in I. And EI. I in I. So this is eigenvalues and orthonormal basis for R2n. Okay. So we get an eigenvalues and eigenvectors for H naught. Okay. Now I define I1 to be all those I such that lambda is positive. I don't need no need to take mod. Lambda I, and it's invertible, so lambda I cannot be 0. Okay. lambda I is greater than 0, less than 1. Okay. And I2 equal to all those I such that lambda I is of course equal to 1. Where it acts on the eigenvectors, where it acts as identity. I3 is equal to all those I such that lambda I is greater than 1. Okay.
So can you explain from and what are we trying to do?
We are trying to
in this
prove.
particular-
So we are trying to prove the. Let me start. We are trying to prove the following. Any symplectic isomorphism will look like U1, SCA, U2. Okay. Now we have written S. So for that we have to prove S naught is equal to some U1 naught times SCA naught, something SCA naught, and U2 naught. That's what we have to prove. You want to prove something for the real corresponding real in S and S naught, there is a one-to-one correspondence. There is a bijection. Okay. So we want to prove something for S naught. So now any S naught can be written as U naught H naught, polar decomposition, where U naught is a unitary and also symplectic we have proved. Okay, because using the uniqueness of polar decomposition, we have proved that it is also symplectic. So we can worry, we don't, so that U naught will give rise to a unitary operator. Okay, that U naught will give rise to a U, which is a unitary operator by the observation we have made. Okay, so we only have to deal with H naught. So I want to write H naught in that form now. Okay, so once I have written, I want to say H naught is actually looks like SA up to a unitary. I in fact, this is what my aim to prove. I will erase it. I want to prove H naught will look like V of some other operator, SA times V inverse, where V is a unitary. That's what I will prove. Once I prove it's enough. You can take this U, attach this U with that V, you will get U1, and V inverse is the U2. Okay, so that's what we are trying to prove. For that, we are going to take, I want to say that up to a unitary, it actually looks like SCA. This is just the conjugation, right? V SCA, V inverse. See, here we want to have a SCA, our RCN. What is our CN looks like RN, direct sum RN, right? But then this place, there may be a unitary, which yes, you can, if you use the V, that it's this R2N decomposed into two subspaces, which are one is an n-dimensional, the other one is like n-dimensional. Okay, and where it acts as some operator A, operator A inverse, but that may be in a different, that may not be like Rn direct sum Rn. It will be clear. That's what I mean. So we want to bring it like this. Okay, so that is where this V is used. Okay, it will be written clearly. But this geometrically, you want to understand it. This unitary is just change the position, right? Unitary will preserve the orthogonality, everything. This is the conjugation by unitary. Okay, but the position will change. You write subspaces. You have Cn or R2n, R2n, which is actually like Rn direct sum Rn. Okay, I will show that this H naught. So on this, we want to get this H naught as A here and A star inverse here on the other part. That is how we want to get it. Okay, but actually this H naught will actually look like some other R2N will decompose into some other Hilbert space like H naught. This H again, I'm writing H. So I want to use some notation for V also I'm using. I want to know some K, okay? Some K direct sum, some K perp. Okay, where K will look like Rn, K perp will also look like Rn. But their position is different. They are not sitting as Rn and R2, Rn direct sum ion. So to bring it to this position, you use a unitary. That's what unitary will do. Unitary will take orthonormal basis to orthonormal basis. It will take orthogonal subspaces to orthogonal subspaces. Orthogonal direct sum to orthogonal direct sum. Okay. So and you can see that is how it will look like. See, I1 is something lambda I. Okay. So and you define K as you have given me K, I will use K. That K1 is equal to span of EI, I in I1. Okay, I take all the eigenvalues where it is less than 1. Okay, all the eigenvalues greater than 1. This H is invertible. H acts as on all, H acts as on this K1 and K2, maybe Ki, again I'm using I is a, maybe I will use K1, K2. K1 and K2 is equal to span of EI and I in I2. Similarly, K3 equal to span of EI, I in I3. Okay. So, of course, H0 will leave K1, K2, K3 invariant because it takes those bases to scalar times that. They form the eigenvectors. Okay. So, H0 will act on EI as lambda I EI. But how will H0 inverse will act on that? That will act as 1 by lambda I, right? That is how H0 inverse will act. But then H0 inverse will, but on the other hand, H0 will act as, all I want to say is, we have this relation, J, H0, J inverse, we have, is equal to H0 inverse. Okay. Now I want to claim is the following. Claim. J from K1 to K3 is onto. Okay. J maps K1 to K3 onto. It maps K1 to K3. I want to say. And J from K2 to K2 is unitary. J maps K1 onto K2 and it maps K2 onto K2. It leaves K2 invariant. That's what I want to say. Okay. And that is clear. So proof of the claim. So you take, let I be in I1. Okay. Then J of EI. You take J of EI. Okay. H0, acting on H0. J inverse of EI.
So first I write EI as.
I take I3. Huh?
You have to write EI as X plus Y.
Yes, X plus Y. Why?
Like R2N, no, like J will be on.
No. EI is just, I am saying it's a orthonormal base. EI is an orthonormal basis for R2N. Okay. Yeah. EI comes from that R2N. Okay. So you take, okay, J inverse. Okay. Or H0 inverse. Let me take H0 inverse. H0. Okay. No problem. J EI, J0 inverse. Okay. Maybe from K3 to K1, both are same. I said K1 to K3, but K3 to K1 is also fine. J is not self-adjoint. J inverse is not J. There is a minus sign. Okay. So J inverse is minus J. Up to that, it's okay. So, J will take EI to, let's see. So you take this, then that is going to be what? This is equal to H0 inverse of EI. Okay. Which is equal to 1 by lambda I EI. No, I want to do, wait. Let me see this. J of EI, H0 acting on this. That is equal to J inverse H0 inverse J, right? H0 equal to J inverse H0 inverse J, right? J, yeah, this is okay. H0 inverse J acting on JEI. There will be a minus sign, no? Okay, minus, let it be there. So what? JEI. Okay, here you have JEI. J square equal to -1, right? No, J square equal to, no, J square is not -1. Okay, let me use J inverse itself. Okay. Let's see, J inverse EI. Okay. So this is just J inverse of H naught inverse of EI, which is equal to J inverse of 1 by lambda I EI. Okay. And which is equal to J in 1 by lambda I J inverse EI. Okay. So if lambda is an eigenvalue of EI, then 1 by lambda I J inverse EI is the eigenvector with 1 by lambda I. Okay. From this, it is clear that these statements are clear. K1 has orthonormal basis EI with I coming from I1. Okay. Where lambda I is less than 1. Okay. And K3 is spanned by EI with I coming from I3, where lambda I is greater than 1. Okay. So if EI is a basis for K1, then J inverse EI or JEI, whatever. I mean, JEI is the, it doesn't matter whether J or J inverse. There is a, I want it to be better to be J from K1 to K3, right? J or J inverse I should use. Oh, that's okay. J inverse. So if EI is an orthonormal, EI is an eigenvector with eigenvalue less than 1. I mean, if EI is an orthonormal basis is greater than 1. Okay. Then J inverse EI is an orthonormal basis with less than 1. Okay. Same thing, right? This okay. So that implies J, if EI is an orth, so EI is a basis for K1, JEA is a basis for K3. And K2 is fixed under J. Because of this claim, right? Because of what we have verified. This implies if EI eigenvector with lambda I, eigenvector with eigenvalue lambda I, then JE or J inverse EI is eigenvector with eigenvalue 1 by lambda I for H naught. Okay. Now we have defined K1, K3 in terms of that. Okay. So if EI spans K1, JEA will span K3. And J leaves K2 to K2. It's a unitary. It will go from K2 to K2. Okay. So now notice that. So in K2, if if we take any vector xy, for any vector xy, okay, you take the jxy, this inner product. This is just going to be xy, and this is just going to be y minus x. This is 0. This inner product is 0. Okay. So this implies EI and JEI are always orthogonal. That implies, so then if EI, I and I2, okay, span of this is equal to K2, okay. If EI is a EI and JEI, both are in K2. EI has an eigenvalue with 1. JEI is an eigenvalue with 1 again, because 1 by 1 is 1. Okay. They are both in K2 and they should be orthogonal. Okay. So we can take a basis. So we can choose basis EI. Let me not index it again. Okay. This I2 will be changed to something else. Okay. I2 is divided by 2. Okay. That set has to be half of that set, where JEI let me call it as I, I22. Okay. You take half of that set basically. Okay. Where EI, and if you take a vector EI and then take JEI, that will give the basis, can choose basis for K2. Okay. Now you take, let M1 is equal to span of EI, I in I1 and I in I22. And M2 is equal to span of JEI with I mean again in I1 and I in I22. Same thing, same index by the same thing. Okay. Then M1 and M2 has the same dimension. They are indexed by the same thing. And M1, J from M1 to M2 is unitary onto unitary. Okay. J maps M1 onto M2. And they have the same dimension. And M1 direction M2 is equal to R2.
How can I be in both I1 and I2?
Say it again.
How can I be in both I1 and I2?
I'm taking the whole I1 union I2. That's what I want to say. Okay, I want to index, take the union basically. Okay, I1, I is an I1, disjoint union I2. Okay. Disjoint union I22, not I2, I22. Half of I2. I mean, I do all these things so that one space is generated by EI, the other space is generated by JEI.
You get orthogonal.
Exactly.
Okay.
The point is EI is an EI is an eigenvector with eigenvalue lambda I, then JEI is an eigenvector with eigenvalue 1 by lambda I. That is what that relation shows. J of H naught J inverse equal to H naught inverse. That relation shows that. Because of that, you get this. So you get in M1 and M2 where J maps M1 to M2. Okay. Now it's clear what to do. Now define V naught from R2n to R2n. I want to take this M1 to the first part Rn and M2 to the second part Rn. Okay. So that V naught of EI equal to I say Fi. Fi 0. Where Fi is an orthonormal basis. Any orthonormal basis. I mean, you can take the usual orthonormal basis for Rn. Okay. And V naught of JEI is equal to 0 minus Fi. Okay. Then V0 maps M1 onto Rn direction 0. Okay. And M2 onto 0 direction Rn by this definition. Now we just want to see how V naught now V naught H naught V naught inverse, how it will act. Let me use the definition. V naught acting on V naught H naught. V naught, H naught, V naught inverse acting on Fi0. Let's see how it acts. Okay. That is equal to V naught, H naught. So Fi, that will go to Ei, right? Ei. And we know that that is equal to lambda I Ei. Okay. So, which is equal to V naught of lambda I Ei. Again, lambda I, which will go to lambda I of Fi0. Okay. So this Fi0 is an eigenvector with eigenvalue lambda I for V naught, H naught, V naught inverse. Similarly, V naught, H naught, V naught inverse of 0 Fi. Okay. This is equal to, suppose V naught, H naught. V naught inverse will become JEA, right? And JEA, we know how it acts. This is equal to V naught of 1 by lambda I. Okay. 1 by lambda I, JEA. Now V naught acting on JEA is just going to be 1 by lambda I, 0 minus Fi. Okay. So we know how it acts on that. Further, you can verify that. Further, see, notice that J of Fi0 is going to be 0 minus Fi, right? So this implies V naught J V naught inverse, okay, is equal to J itself. So V naught is symplectic. Okay. V naught is symplectic because it satisfies this. And V naught, H naught, V naught inverse look like that, right? V naught, H naught in V naught inverse looks like lambda I on those eigenvectors. See, I have just verified V naught, H naught, V naught inverse acting on Fi is lambda I. Fi generates Rn, right? This Fi, this thing, this Fi0 generates Rn. This 0 Fi generates the other part of Rn, right? And on that it is lambda I. On that it is 1 by lambda I. Right? So this so V naught, there exists a in M and C such that V naught, H naught, V naught inverse is equal to A 0 0 A inverse, right? Because it acts as lambda there, it acts as 1 by lambda I, right? Correct?
Sir, I think you missed a minus.
Ah.
Little bit higher, like on.
Here, where minus?
V naught, H naught, V naught inverse of 0 minus Fi.
Wait a minute.
Because you defined V naught of JEI to be 0.
Correct, correct. That shouldn't be a problem. Wait. Yeah, it should be a minus here. Good, correct. It should be a minus here. Okay, now it's okay. Yeah. That is JEI, correct. So JEI and it becomes minus. Okay, it's okay. Okay. Now you can remove the minus and you can note that, I mean, so with, I don't want it with a minus. So this implies V naught, H naught, V naught inverse of this vector 0 Fi itself is equal to 1 by lambda I 0 Fi, right? So they form an eigenvector on that. So this implies that there exists a single operator A in M and C, M and R. I am always writing. See, this so used to this complex numbers M and R such that V naught, H naught, V naught inverse is equal to A0, A inverse. It looks like this. Okay. So H naught is equal to, of course, V naught inverse. I mean, this is a SA inverse. Huh? So which is equal to SA of naught. Okay. So H naught is equal to V naught inverse SA naught V naught. And our S naught is equal to, we had original unitary U naught, okay, and V naught inverse SA naught V naught. So call this as U1, call this as U2, and maybe U1 naught, U2 naught. Okay. Then S is equal to U1 SA U2. Done. Good. Okay. Shall we stop or shall I go for some more time? Because I don't know how much time I will be having on Friday. I haven't lost my energy, so maybe. Okay. So, okay, I will recall next time. So I have to say something more on this thing, but it will be nice to recall everything. Use this theorem and recall. Okay. In particular, we can, anyway, so let us make this definition clearly. So we know that if we want to define gamma of SA. Okay. I have already given you an assignment. Gamma of SA from gamma of Cn to gamma of Cn. If you are given a in MNR, real n cross n real linear real matrix, then you can define SA, which is symplectic. So gamma of SA, you can define it as, this is also same as, of course, L2 of Rn. You are identifying this is the L2 of Rn. So gamma of SA acting on any F at X, you want to verify. This X comes from Rn. Okay. This is equal to 1 by determinant of A, which is not equal to 0 because it is positive, because it's invertible, and F inverse, F of A inverse X. That's all. Okay. Then gamma SA is invertible. Okay. And gamma of SA, W of alpha, gamma of SA star or inverse, whatever you want, is equal to W of SA alpha. This is assignment. Okay. Just verification, direct verification for assignment. Okay. And further, it's also true that and any xi gamma of A, gamma of SA, SA xi is greater than 0. Now for general S symplectic, S with S is equal to S is equal to U1 SA U2. Okay. Define gamma of S is equal to gamma of U1, gamma of SA, gamma of U2. Okay. Where this is, gamma of SA is well defined. Gamma of U1, gamma of U2, second quantization exists for unitaries. That is second quantization for that symplectic, which you can define. Okay. Then, sorry, this is not phi. This is the E of 0. I'm sorry. That doesn't make sense, no? What I have written. E of 0, E of 0. This is not true. Yes, that's not a positive operator. E of 0. That's only for that vector. I fix that condition to get a unique, for the uniqueness. Okay. Then E of 0, gamma of U1, gamma of SA, gamma of U2. Okay. E of 0 is equal to gamma of U1, you can take it this side. which is equal to gamma of U1 star E of 0. Okay. Gamma of SA, gamma of U2 of E of 0. Okay. Now gamma of U1 star is E of U1 star, which is just 0, E of 0 again. Gamma of U2 is 0, that's also E2. So this is just E of 0, gamma of SA, E of 0, which is again greater than 0. Okay. So whatever we have defined, gamma S satisfies this following. So E of 0, gamma of S, E of 0 is greater than 0. Now proposition. Given for S symplectic, there exists unique gamma of S unitary such that gamma of S W of alpha, gamma of S equal to W of S alpha. Okay. We already know that this property satisfied by second quantization of unitaries. And we know that it's already it's also satisfied second quantization of SA, which you can second quantize. But yeah, SA can be written like this. So this is satisfied. We have got the precise definition for gamma S now. Okay. And E of 0, this uniqueness only we have to define. Here you prove is greater than 0. Okay. Proof. Only uniqueness. Only uniqueness has to be proved. Other things are clear. So suppose there exists another U, maybe W, from the Fock space, comma Cn to comma Cn. Okay, such that maybe I will use V. W is confusing. V W of alpha, V star is equal to W of S alpha. Okay. Now this is also equal to gamma of S, W of alpha, gamma of S star. So this implies gamma of S star V, okay, W of alpha. Okay. These two are equal. Okay. Gamma of S star V equal to W of alpha itself. Okay. So that is gamma of S star W V commutes with W of alpha for all alpha in Cn. Okay. So it commutes with every operator because W of, see, you should note something. I have to say that this, if Sn converges to S, okay, then SNT converges to ST. Sn converges to S strongly. Then SNT converges to ST strongly. It's not true in both the way. I mean, actually for nets, actually, for sequences, it may be true. I don't know. Okay. This strong continuous is not jointly continuous for the product. Norm is jointly continuous. Sn converges to S, Tn converges to T. Then Sn Tn will converge to ST. That's not true for strong convergence. But if you keep one of them as it is and then vary the other one, vary the sequence, then it will converge. Okay. But here, this W of alpha strongly generate B of H. Okay. So there will, right? It will strongly generate B of H. So I'm again and again. Okay. Okay. So if something, so if something commutes with the generated W of alpha, it will commute with everything. Because everything can be approximated by linear combination of W of alpha. If something commutes with W alpha, it will commute to the linear combination. Okay. And when you are using only one, in the commutative verification, you are using only one of them. Right? Suppose you want to verify that gamma, whatever the gamma S star V commutes with all W of alpha. You want to verify that gamma S star V commutes with any arbitrary T. That T can be strongly approximated by something. Some net. Okay. Then the commutator, this works. This property works. So because of that, if it commutes with the generator, it will commute with everything. This strongly generated algebra. So both see, this is also equal, right? So I have just said gamma S star V commutes with everything. So it should commute with everything. Okay. So this implies gamma S star V is a scalar, okay, equal to some lambda with lambda in C, of course. With mod lambda equals 1. Okay. Now, this property gamma S, this property E of 0 and something dot E of 0. It is satisfied by both V and gamma S is greater than 0. Imply that lambda has to be 1.
So why did you need to mention this SN convergence is strong? Because
I am using the fact that something commutes with all W of alpha, then it commutes with every operator.
but we have already shown that it becomes the ball as well, it has to be X.
That is because of this.
Yeah.
We have shown means we haven't really. The proof is this because you are using this. Otherwise, you will not get.
I mean, also if you know the strong closure of W alpha is B of H, then the commutator of W alpha will just be scalars, right?
Commutator, yeah. For that, you are using this property. Without that, I generally mentioned, but for that you are using this property. Strong convergence is preserved of. If you fix one operator and the product is continuous, product map is continuous. That's what it says. Okay. When you fix one of them, the product map is not jointly continuous. Okay. That is why this. So we have fixed an operator uniquely. Okay, we have well defined. We have this gamma. See, I want to well define this gamma second quantization. So this way we have a well defined map. Okay, we cannot have a map up to alpha or something. So we got a map which is well defined. Okay. Now let us see whether it satisfies some more property. I said something, it may not be correct. So I still have time to prove it. Let's see.